Okay, so new chapter. This is 5.1. In chapter 5 is dealing with systems of linear equations. So a little bit of background with it. There's going to be some notes that's got a definition of systems in it, but systems of linear equations are when we have two linear equations. And what we are going to find with systems of equations is we are going to find where these are the same. So let's say I have an equation here for this line and an equation here for this line. Just a little review. Now, if you guys were in person and I would ask you, how would I tell that that point lies on the line? That is a solution to it. Remember, points that lie on a line are solutions to the equations, meaning if I took this xy ordered pair and plugged it into whatever equation this line was, I would have to get a true statement. If I took this ordered pair and plugged it into the equation of this line, I would get a false statement because this point don't lie on that line. You get true statements when you plug in the xy ordered pairs. When you plug in the xy ordered pairs, you will get a true statement. It means it lies on the line. When we are solving systems, and we're going to do that by graphing today, system is just two or more linear equations, and we are looking where these are the same. The only point that lies on both of these lines is where these lines cross. It's the intersection. This point's special because if I plugged it into the equation of this line, it would give me a true statement. And if I plugged it into the equation of this line, it would give me a true statement, meaning that this point lies on both lines. It's the intersection, and that is what we are doing. So in these first six, it says, tell whether the ordered pair is a solution of the system. Point being on this one, in order to be a solution to the system, it has to be the intersection. The xy ordered pair that is given as the solution must give me true statements for both. So what do? You have an x, you have a y. Plug them in. 3 plus 1. Does 4 equal 4? It does. That checks. If x is 3, 2 times 3 minus 1. Does that equal 3? Well, this is 2 times 3. I can see already. Does 5 equal 3? No. That does not check. Is this a solution then? No. It lies on this line, but it doesn't on this line. And in order to be a solution, we are looking for the intersection, and we know that intersection has to make it true for both because it's the only point that lies on both lines. I would take 1 and 3. X is 1 minus 3. Does that equal negative 2? Well, 1 minus 3 is negative 2. That checks. 2 times 1 plus 3. Does that equal 5? Well, that's 2 plus 3. That equals 5. It checks. And when it checks in both, I know it lies on the line. You have an X. You have a Y. You want to know, is this the solution to this system? Is this the ordered pair where these two lines cross? I can certainly check it without graphing. If x is 2 and y is 0, 2 minus 2 is 0, 0 equals 0, that checks. If y is 0, negative 3 times 0, negative 3 times 2 because x is 2 plus 6. 0 would equal negative 6 plus 6. That is indeed 0. It checks in both. It's a solution. There's your x, there's your y. Just be careful when you got the negative negatives. This top one would be negative 1 minus 2 times a minus 2 is equal to 3. Negative 1 plus 4, does that equal 3? It certainly does. It checks in the first. In the second, 2 times negative 1 minus a minus 2, does that equal 0? Minus minus slash slash, negative 2 plus 2, yes, that equals 0. I get true statements for both, and it lies on the line. X and Y, 3 times negative 2 minus 2 times 3, does that equal negative 12? Negative 6 minus 6 is equal to negative 12. Negative 6 minus 6 indeed equals negative 12. 2 times negative 2, whoops, that's not a plus, that's a minus. 2 times y, which is 3, does that equal negative 12? Negative 4 minus 6, does that equal negative 12? It does not, because negative 4 subtract 6 is negative 10. It doesn't work there. No, that ain't no solution. X and Y, plug them in. Is it okay to do these mentally? Sure. And I'm going to do this one mentally. This is how we do it though. X would be 4, so that would be 8 minus 6. 8 minus 6 is indeed 2, that checks. 12 minus 3 times 3 plus 9, 21. 12 plus 9 is 21. That certainly checks, and yes. So there we go. Point being, it's got to be true for both equations because we are looking for the intersection, and the only point that is going to be the same or give you true statements is the point that lies on both of those lines, which is the intersection. There are going to be some like this where you're going to be given a graph and you're going to be asked to use the graph to solve the system. Remember, use the graph to solve the system. You're looking for the intersection. The solution is an ordered pair. You're not in here. You're not in here, dude.
Oh, yeah.
Shut that door, please. Sorry about that. Eeh. Intersection. Right there. That's the solution. What is that ordered pair? That's what I'm looking for. To the right 2, down 2. 2, negative 2. And you're always going to want to check this. Easy right here. What's 2 minus 2? 0. That checks. This one would be 6. Minus 2 times minus 2 is plus 4. Does that equal 10? Yup. It checks. And I'm going to box it in. I will get this ordered pair. It is negative 1, down 1, 2, 3. Negative 1, negative 3. Does it check? Well, negative 1, negative 2 times a negative 3, positive 6. Negative 1 plus 6, 5, it checks. Negative 2 minus 3, that indeed is negative 5. It checks, and I'll box it in. You're going to want to check these because we are going to actually graph these lines, and you may get an intersection that's a little off, but you'll know it's off because when you check it, you won't get a true statement. These are nice and graphed, right on the money. To the right 4, up 2. I have the ordered pair 4, 2. Is that a solution? Well, it'd be 4 plus 2 times 2, which is 4. That's 8. That checks. 3 times 4, 12. Minus 2 times 2. 12 minus 4 is 8. That checks, and I got it. Point being, solutions to systems of equation, linear equations, are ordered pairs. Is an ordered pair. You're going to have one of them. I'm going to flip this over. Now this is the bulk of them, and how we're going to spend some time graphing. We could all use some help graphing. When we graphed before though, you needed 2 points to make a line. I'm going to tell you, you are going to want to get more than 2 points and be accurate with your graphs. We're not going to go back and review a bunch of graphing. Hopefully we know now y equals mx plus b is going to be our go-to. These look like y equals mx plus b, so I can easily identify my slope as -1, or -1 over 1, and my y-intercept of 3. My slope is 1, or 1 over 1. My y-intercept is 3. I am graphing these two lines. I am going to be very accurate, and I'm going to get the intersection. Once I have that intersection, I am going to plug in those ordered pairs to test it and make sure it is the solution. B of 3, right there. Down 1 over 1, negative slope. And I'm going to continue this down, making these points. And I'm going to continue it up, making these points. Why am I putting multiple points on there? Because I'm hoping that when I graph this other one, I get a point that they have in common. I will make this line go through there, looking for the point that's going to intersect. There's my first one. Slope of 3, or slope of -1, y-intercept of 3. This one has a y-intercept of 5. And now I'm going rise of 1, run of 1. So I'm going up this way. It's coming back this way. But I know I can also go, oh, whoops, I put that on 4. That would have created some issues. It goes on 5, which is up 1 over 1. Now I can see I can also go down 1 over 1, down 1 over 1, and continue this line back, and I can see that the intersection of those two lines occurs at that ordered pair right there, and that is at -1, +4. I'll test it. Well, if I want y is 4, -1 is +1 plus 3. 1 plus 3 is 4, that checks. I want 4 to equal -1 plus 5. -1 plus 5 is 4. That checks. I'll box it in. 1/2 x plus 2. M of 1/2. B of 2. M of -1/2. B of 4. Graph them. Y-intercept of 2. Rise of 1, run of 2. Rise of 1, run of 2. I also can go down 1 to the left 2. I've got this line that goes right there. I'm going to look for the intersection, and notice I put multiple points. A B of 4, a slope of 1/2, rise of 1, or I'm sorry, this is a -1/2, down 1 to the right 2, right there, down 1 over 2, also up 1 over 2, but I'm not that concerned because when I go in this direction, right here, I have that ordered pair, which is 2, 3, and I'll check it. I want to know, is 3 going to equal 1/2 of x? Well, 1/2 of x, half of 2 is 1. 1 plus 2 is 3. That checks. I want 3 to equal -1/2. That'd be a -1 plus 4. -1 plus 4 is indeed 3. It works, and I box it in. I 100% get that this is in standard form, and I could probably use intercept form to get it, but I think our go-to should be y equals mx plus b with these. I'm going to solve for y just to be consistent, which means I would subtract 3x. -2y then would equal -3x plus 6. I would divide everything by 2. -2, which leaves me with y is equal to 3/2 x minus 3. I will go ahead and plot that at -3, a slope of 3/2. 1, 2, 3 over 2. 1, 2, 3 over 2. And I've got that line right there. My second line, y is equal to negative 3. Oh, look at that. A horizontal line going through 3 on the y-axis, a negative 3, and I have an ordered pair right there. That is the ordered pair 0, negative 3. Test it. If x is 0, that would go away. 6 divided by negative 2 is negative 3. That certainly checks. And then I know if y is negative 3 certainly equals negative 3. That's right, I'll box it in. I would take a second on your own and try to get these graphed and see if you get it. Go ahead and pause the video, try to do these next 3. My m is 4 on this one, my b is 0, m is negative 4, b is 8. I'll graph them. Y-intercept of 0, rise of 4, run of 1, rise of 4, run of 1. And I've got this line that goes right there through the origin, continues on back there. I'm hoping I get an intersection here. 8 is my b. There's 6, 7, 8. Down 4 over 1, negative slope. 1, 2, 3, 4 over 1. There's my intersection. 1, 2, 3, 4 over 1. I will continue it for continuity's sake, but I know my intersection is right there, and that is at 1, 4. I can certainly check that. 4 is equal to 4 times 1, 4. That checks. 4 would be equal to negative 4 plus 8. Negative 4 plus 8 is 4. It checks in both. I'll box it in. B of 3, slope of 1/4, up 1 to the right 4, down 1 to the left 4. 1, 2, 3, 4. I have this line right here. Up 1, 1, 2, 3. I missed that point. So I've got this line for my first one. And for my second one, I have a b of 5. There's 5. Up 3 over 4. I'm going up in this direction over here, which means I don't want to be off my graph, so I will go down 3, 1, 2, 3, to the left 4, 1, 2, 3, 4. Bingo. There's my intersection. Had to go in the opposite direction. That's at negative 4, 2, and you can certainly test that in and check it. If you want this to be 2, negative 4 divided by 4 is negative 1 plus 3. Negative 1 plus 3 is 2, it checks. Plug in y is 2. 3/4 times negative 4, well, that'd be negative 1 times 3 is negative 3 plus 5. Negative 3 plus 5 is 2, it checks. I'll box it in. Now on this last one, we got to be careful because you will get some that your graphs have to be extremely accurate. This doesn't lend itself nicely to intercept form because 7 is prime and it's not evenly divisible by 3 or 4, and neither is this 3 divisible evenly by 5 and 2. I'm going to solve for y on both of these, so I'm going to subtract 3x. Negative 4y is equal to negative 3x plus 7. I would divide by negative 4. Y then is equal to a positive 3/4 x minus, 7/4. Doesn't tell me a lot, but if I use it as 1 3/4 or negative 1.75 for my b, it's a little bit more helpful. So you have a slope of 3/4 and a b of negative 1 3/4. For the second one, I got 5x plus 2y is equal to 3. I would subtract 5x. 2y then is equal to negative 5x plus 3. I would divide everything by 2. y is equal to a negative 5 halves x plus 3 halves, or 1.5, or 1 1/2. Graph these. This is what I'm looking to graph. Negative 1 3/4. That's almost to negative 2 right there, right? This would be halfway. That's halfway again. And now I have to go up 3 and over 4. So I know I'm going to be over here on the 4, but my up 3. I got to be careful when I'm going up, because here I'm at the, the 3/4. So you're going to want to go up that 3. So you'd be here 1, here 2, and then right above this line would be 3. And now I would be over 4. 1, 2, 3, 4. It is that point roughly right there. Because this isn't graphed using quarters, it is an estimation, which is okay. If I'm at 1 1/2, here's 1. 1 1/2 is right there. Now you are going down 5 over 2. 1, 2, 3, 4, 5, and then over 2. And I get that line right there. It's not exactly on those crosshairs, but it is darn close to that point right there. 1, -1. Test it. Test it. I'm going to test it right back in my original equations. If x is 1, this is 5 minus 2, because y is -1. 5 minus 2 is certainly 3. It checks. If I plug in 1 here, this is 3. Minus 1 times a minus 4 would make that a plus 4. 3 plus 4 is 7. It checks. Even though your line may have been a little off here, which it could be, estimate it and then check. We're going to get into some ones that are a little bit more complicated, but that is good for now. I don't like the graph on this one. There's a couple of different ways to do it, but we're going to certainly get into more story problems as we go ahead.